design and construction support. Pascal holds a PhD from UBC and an MEng from the National Polytechnique Institute in Grenoble, France, currently based in Vancouver. So just my little bit of intro here, sort of think about it. In Canada, most of our critical linear infrastructure, like railways and the highways, tend to parallel larger rivers, which means they also tend to cross all the smaller streams and creeks and trickles. We used to say that there were an untold number of these smaller crossings that need to be conveyed through embankments. And railway and highway owners always knew that anytime there was an embankment at a crossing like that, there could be a washout. Obviously, for many reasons, washouts are bad. In this presentation, you'll see some important advancements in estimating much more precisely than we ever could where and when washouts could occur. These advancements will surely help owners manage risk to our most critical highways and railways. Over to you guys.
We got our system working here. Thanks, Dave. So the talk that we're giving, the tagline was harnessing the power of multi-scale data sets, remote sensing, and first principle hydrology and hydraulics to develop a risk-informed asset management tool for railway embankments with the objective of mitigating losses from flood hazards. That's a pretty exciting title to me, and a pretty exciting photo there of what happens when you have a very dramatic washout. So partial funding support for this project came from Transport Canada's Rail Climate Change Adaptation Program. And although Pascal and I are presenting on this work, it wouldn't have been possible without the support of the CN team, including David Brown and Trevor Evans. The methodology, analysis, and results are the results of contributions from many individuals at BGC, including Joel Wortley, Patrick Grover, who you've heard from earlier, Sterling Mitchell, Daniel Westbrook, and Zach Sala. So I guess starting off is, what is a washout? So here we're defining it as embankment failure due to water flowing through or over the embankment. We're looking at hydraulic erosion of the soil and rock that support the railway. And this can occur anywhere along the railway where water is directed over or through the embankment in sufficient quantities to cause erosion, and provided that the flow is sustained long enough to reduce the structural integrity of the bank. So we're looking at watercourse crossings, and we're looking at culvert locations and trying to identify those locations which are more likely to exceed their conveyance capacity. In this context, we're looking at railways, and our concern is impassable track, but washout of embankment can apply to other types of linear infrastructure like highways. With this project, we're not looking at structural culvert defects or channel erosion, just that conveyance capacity. So what conditions might lead to a washout? Here we can be looking at high inflow. So if you have a large storm event creating a lot of runoff, maybe the culvert is too small to carry the flow. Perhaps the culvert is blocked with debris. You have the potential for looking at the debris availability and the transportability and the size of that debris versus the dimensions of the culvert. And then you have the issue of ponded water, and that water then seeping through the embankment, leading to internal erosion of the embankment. So why is this a problem? Here we're looking at damage to the embankment, and then leads to impassable track, and that has operational consequences. So you could have workplace injuries or loss of life, track closure time, and that can result in loss of revenue to the railway owner and delays in the transportation of goods to customers, as well as emergency repair costs, which are always more expensive than scheduled repairs. So washouts are a significant source of risk for CN. They have a rail network of about 32,000 kilometers across 2 large countries. There's culverts in the tens of thousands, and we're looking at climate change. So there's a need to identify the critical system constraints. So I'll pass this on to Pascal here to take us through the details of the project.
Thanks, Rebecca. So what are we doing about this? So the challenge here is to develop the risk informed washout assessments to evaluate the potential for washout hazards at those sites. In today's presentation, you see the risk formulation at the bottom, and the first two terms are the terms that I'm going to be focusing on today. So the first two terms are the probability of ponding and the conditional probability of washout given ponding. And why we just don't consider the probability of washout is that ponding, as Rebecca explained before, is a pretty key component to estimating the stability of the embankment. So how do we access ponding levels? We need to model the inflow coming from the upstream watershed, the storage capacity in the ditch that's upstream from the embankment, and then the flow conveyance capacity of the culvert or culverts if they're present. The first step in building the ponding model is to estimate the watershed inflow. And through the presentation of Patrick and Evelyn, I think you had a glimpse of how we were trying to do this. But the process here was to automatically delineate continuous watersheds along the railway embankment and extract characteristics of the watershed and hydrographic network. We then used a high-resolution LiDAR within a band running along the alignment of the railway embankment to extract the embankment geometry. That's what you see a cross-section at the bottom. And the stage storage curve of the upstream ditch along the railway embankment. That's going to be pretty key to estimating the ponding levels. So the hydrologic model at each of these sites comprise 4 elements: the upstream watershed, the upstream ditch, the embankment, and the culvert if present. In this approach, the process was mostly automated to make the assessment scalable and applicable to system-wide problems. So the synthetic rainfall events that I mentioned before were derived from available rainfall intensity, duration, frequency, or IDF data, estimated either at point data, so weather stations, or as gridded products of reanalyzed precipitation data. The key advantage to following this approach is that there are existing corresponding climate-adjusted IDF products, which allows for the comparison between the historical and climate-adjusted conditions. We'll get to this a bit later. So in this figure, we show an example of those historical and climate-adjusted IDF curves used as input to the washout model. BGC developed those climate-adjusted IDF data based on Cordex datasets. And so there are several datasets of projected precipitation data. But unlike most, this one is dynamically downscaled, which allows to capture convective precipitation events. These are small, intense, fairly large, very small footprint and short duration intense events, which are pretty useful in driving flood events for very small watersheds. So now onto the results. We tested the approach on a proxy railway system, which intersected about 1,100 watersheds. On the figure to the left, we show individual base annual probabilities of washouts. A value close to 0 indicates that the probability of washout is low, and a value close to 1 indicates that that probability is high. At this stage of the analysis, these are not actual probabilities of washouts. These are base estimates that allow for ranking and prioritization of sites, but a system-wide assessment of past washout events would allow for calibration of these estimates. On the figure to the right, we see the exact same data, but this time plotted as a density function. Now the base probabilities of washout are on the x-axis. And we see 2 conditions in blue for the historical conditions, and in red for the climate-adjusted conditions. So we see that for each of these two curves, let's start with the historical condition, that the majority of the sites are located on the left side of the figure, where we've got the highest density. And so that left part of the figure is characterized by a lower probability of washouts. This suggests that most sites on this system are featured with adequate flow conveyance capacity, like so big enough culverts, so that most of the time the residual, they can convey the flow, and so that the residual washout potential is only borne by less frequent, larger magnitude flood events. On the right side of the same figure, we see fewer sites that are characterized by a higher probability of washouts. For these sites, the washout potential also exists for more frequent, lower magnitude flood events. So these are the sites that are of greater interest and concern to us. Under the climate-adjusted condition, the pink curve, we anticipate that that number of concerning sites will increase. So what are the next steps? Well, first, we'd like to apply this framework. So this is more of a proof of concept, but we'd like to apply that framework to the CN subdivisions as part of the RCAP project. We've completed assembling all the data that required to run the model, and we'll be doing this in the following weeks. And then what else? Well, as we collect additional field data, we'll be able to run postmortems on observed washout events, which can help inform the calibration of the base estimates of washout probabilities that were shown on the graph before, and also develop site-specific and regional operational rainfall thresholds, something that Pat and Evelyn touched on before. In the same vein, washout hazard can be predicted by fitting the current framework with a short-term prediction forecast of precipitation. This hopefully can help our clients inform operational decisions. This concludes our presentation. Thank you for your interest, and we welcome any questions.
I've got the blue circle of death in the chat window, so I'm not sure if anybody's put any questions in the chat. I know, Gemma, maybe you can help out there.
Unfortunately, Dave, I'm seeing the same thing you are.
So how about if anybody has a question, they could unmute themselves and go ahead and ask it.
Okay, there is a question that's showing up in the chat. I've got I guess, a better computer than you guys. Did you use a crossing size threshold? Marc Olivier, I don't know if you want to elaborate on that question.
Thanks. Yeah, I was curious if you had like a size threshold where you consider smaller sites that might be impacted by smaller rain event to like all the way to larger crossing where you would have a bridge. So is there a maximum size that would fit inside your analysis there?
Currently, no, but at some point, because the probability of ponding is derived from an actual rainfall runoff model, if one were to consider a very large catchment, I think the current model structure wouldn't be sufficient to adequately model peak flows. But maybe more importantly, there's no bottom threshold. So we can, and there are actually no real definition of crossing. So we don't need an actual channel. We just need ponding behind the embankment and some sort of a catchment upstream to collect the runoff and have it ponded against the embankment. So we don't need a stream network. There's no minimum catchment area to meet.
Well, I guess the challenge that you'll be facing is where to cut off your analysis to how to define catchments that where it doesn't make sense to use a rainfall runoff model, right?
Correct. Yeah. We haven't we're really working with fairly small catchments for 99% of them.
Yeah.
Or more. Yeah. So we'll the larger catchments are edge cases, and we can address them separately.
Right. Well, very cool presentation. Thanks.
Still not seeing the chat, Matt. Anything else in there?
I think you're all good.
Great. I think we have time. I can ask one quick question of you guys. Certainly in Eastern Canada, and I think in large parts of Western Canada, like sudden influxes of water that aren't related to rainfall, such as like beaver dam breaches upstream and like ice out. I'm not sure what the right technical term is for that. Are we setting up a model in a way that can later be expanded to include these kinds of inputs?
Yep, that's the plan. Rebecca, do you want to take this one, or do you want me to?
Nope, I was just going to say, yeah, it's a flexible setup that we can sort of modularly add those different pieces. And I know Pascal is starting to look at just looking at that potential for blockage from things like beaver dams and the kinds of debris and sizes of debris that might be coming down. So it's quite modular.
Nice. Great. Well, yeah, nice job, guys. I guess, Gemma, back to you.
Awesome. Thanks, Dave.